Okay, so now the record is on. You can see this is the design example, but this one is more like the analysis problem. The analysis problem would mean that you are given the section already. We already know what we have, but we would like to investigate its load carrying capacity, so to speak. Okay, so let's see, this is the condition that we have. We have the H 300 by 300 by 94 kilogram per meter, and the grade is SS 400. This is very important for you. Okay, so now you know that you must know that Fy is 2500 kilogram per square centimeter. Okay, now here's the condition. This is the H 300 by 300 by 94, and it has bracing in one direction, as you can see. Okay, if you look at the side view in X direction, there's a bracing, and you can see this symbol, which means that's the back end of the arrow. Okay, so if you flip 90 degrees, you will see the bracing on the side, trying to limit the movement in Y direction. So if I may draw this H in 3D, what you would see is something like this. Okay. Okay, and your brace go in this like that. So hopefully you can see that this one is in this plane, right? The bracing is in this plane itself. So this we talked yesterday about the importance of the bracing. It is anything that can help prevent the lateral movement in any particular direction. So we have the brace in this direction. That means you don't have the lateral movement in that direction. It is prevented. But you can still have the lateral movement in this direction, right? So what do we have there? It means that when you can have the movement in that direction, your compression member can rotate in this axis. Right, I hope that you can see that. That's the best I can do in terms of drawing the 3D object. Okay, so your compression member can dance in that direction, or I can just say, well, it can go like that. All right, but for this axis, you know, when it wants to rotate in this direction, when it wants to rotate in this direction, it cannot do so at the brace point. So when you look at this axis, when it wants to have the lateral movement or buckling in this axis, the deflected shape has to be like this. Correct, because of the bracing. Now I wonder a little bit, something that none of you asked yesterday was that how would we know that whether or not this is strong enough to be the brace, right? There is the part of the specification saying something about the strength and the stiffness of the member that can be considered a bracing, but it's you know, it's just one thing too many for the class as well. But one thing I can tell you is that it doesn't require a lot to be to have a member as a bracing. I don't remember the exact number, but it says that this member must be able to take only 2% of the compression in the compression member itself. So 2% of that, you know, will be enough to work as a brace. So it's not a lot. That means you can almost put any member in there, and then it should be able to help you prevent the lateral movement in that particular point. Okay, so any question regarding this? And one thing I forgot to tell you yesterday is this, and this is quite important for compression member. Any compression member, it's written there somewhere, the L over R of the member should not exceed 200 or it becomes too slender. Okay, even though you may check the strength and okay, we have enough, but you should change the member so that the L over R of the member does not exceed this limit as well. Okay, for practical purpose. All right, so I think we are now ready to do our calculation here. And because this is the analysis problem, we can just go ahead and check the section. Okay, so the first one is of course local buckling. Okay, now please keep in mind that when we do the work, you must use the actual size of the member. Okay, please also be informed that this is not the actual size. It may not be. This is what we call the nominal size of the member. So when you really work, you must check whether or not the width of the flange is 300 millimeter, the depth is 300, and so on and so. Okay, and in this case they are. So we will start by checking on the local buckling of the flange, and that will become BF over 2. That's the width, right? It's BF over 2 divided by the thickness, which is TF. Okay, and in this case, the BF is 300, and then 2 just to split the width of the flange, right? And the thickness of the flange in this case is 15. And this is 10. So we are going to compare this with our limiting value, which is 0.56 square root E over Fy. Okay, E is 2 million roughly, and Fy is 2,500. If you want to take notes, it's 2,500, right? That's 2 or 4, like that. And like I mentioned yesterday, this is roughly 16. So here we are. See, the slenderness ratio of our flange is less than the limiting value. Okay. Now, let's check the web. Now, one thing that you must be aware of is that when you check the web, it is the ratio of H over TW, and H is not the depth of your member. So this has to be 300 minus 2K. And I don't have K here, but K is basically the thickness of the flange plus the radius of the fillet. And right here you have it. Fillet is 80 millimeters and the thickness of the flange is 15. So here is, say, 15 plus 18. Sorry for two parentheses. And the thickness of the web, it just incidentally is 10 millimeters. And this comes out to be 23.4. All right, which is to be compared with our limit, which is 1.49 square root E over Fy. And this is huge because it's 1.49, so it's 42.6, and it's too less. So we can say we now have compact section, and we get what my teacher called the big OK. So what does it mean, ladies and gentlemen? It means that local buckling will not occur before lateral buckling. That's the meaning of it, okay? Like we discussed yesterday. Now, before you make any further notes, let me show you this. In my table, you will see that if we look at the 300 by 300 by 94, it is in fact this one, okay? The compact section criteria has been provided in the table already. And you can see that for the numbers that we just calculated, you see BF over 2TF is 10, exactly the same. And H over TW is also exactly the same. So, you know, keep a good hold on this table because I have developed them to be exactly like the tables provided by AISC design manual. So it has every properties you ever need. And the reason that I show you both the calculation and the number from the table is that if, say, you may have to work with some other sections in other countries in the future, and they may not have something like this for you, you must be able to calculate those slenderness ratios of the elements by yourself. But let's say if you work in Thailand and you use sections by TIS, these numbers are readily available to you. Okay, you can use the table, pick them up, and you see 10, that's 23.4. So your job is actually only to calculate the limiting value. Okay, and K is there as well. We also have K, which is 33, you see. All right, we ready to move on? So you know, now you know these numbers. You can pick them up from the table, or you can do the calculation by yourself. So keep in mind that we have these numbers already, okay, you guys? And it would be really, really sad if you decide to do the calculation yourself and then you get it wrong, right? All right, so now we clear one hurdle, that is the local buckling. It's time to check the main thing, the main event, that is the lateral buckling. Okay, and now you see we have, because this is the H shape that looks like this, so that means we have the doubly symmetric section. It's doubly, right? Okay, not double, it's doubly symmetric, because doubly is an adverb that emphasizes on the fact that you have a symmetric on both axes. So it's doubly symmetric section. And that means we can have lateral buckling in both X and Y direction, depending on which axis is more, has more slenderness ratio, right? So this time, because we have the bracing for the buckling in Y axis, so we better check both, okay? So now we're going to check KL over R in X direction. And because this column is like pin, so K is 1. And the length in X, the unbraced length in X direction is 8 meters. But because the radius of gyration is in centimeters, so I'm going to change the unit here from 8 meters to centimeter by multiplying it by 100. And Rx, that is the radius of gyration, not the fillet. Be very careful. It's this one, right? which is 13.1. So now the slenderness ratio is 61.1 in X direction. Now, am I going too quickly? You hope not. Now it's in Y direction. KL over R in Y direction. So again, because of the pin support, we have K equal to 1. Now in Y-axis, we have the bracing in the middle. So the unbraced length becomes 4 meters. So I have to multiply by 100 to change the unit and then divide this by RY, there, which is 7.51. So here we go. The this is too low. Okay, this is 53. So what does it mean? Now we have KL over R in X direction equal to 61.1 and KL over R in Y direction equal to 53.3. So in which direction the slenderness ratio is greater? It is X, right? So this one governs. Meaning the presence of the bracing makes the X-axis more slender than the Y-axis. Okay, so now we've gone this far. We know that if lateral buckling is going to occur, it is going to occur in the X-axis before the Y-axis because of the slenderness ratio. So the next step is that we need to look at this ratio and determine whether or not it is less or greater than the limiting value, which is 4.71 square root E over Fy. Remember that? And, you know, I'm not going to keep writing this. E is the same, 2 million approximately. And Y is 2,500 for SS 400 steel. And this is 135. So that means, you know, our governing slenderness ratio is less than this value. So what does it mean then? It means that we are going to have the inelastic buckling, right? Your column will buckle inelastically because the governing slenderness ratio is less than this limiting value. If you cannot recall, you can go back to slide and check your formulas. You will have to scroll back up very far. So be patient, okay? There, okay? That's what it looks like. Now we have the slenderness ratio less than this limiting value, so we are in this. Okay? So what are we waiting for, right? We now can go ahead and perform our calculation. So elastic buckling stress, Fe, right? We calculate this first to plug this into the main equation. This is equal to pi square E over KL over R squared. So that becomes 61.1 squared. Don't forget the square term, you know. And this is 5.390 approximately kilogram per square centimeter. Wow, when you see the number for the first time, is this correct? Is that possible? The number of FE or elastic buckling stress is so high, way higher than your yield stress, right? But you take a look at your equation. You take a look at your equation. Here, you see that, oh, wrong one. All right, you take a look at this. The base is less than 1, correct? So when you power some number that is less than 1, if your power is greater than 1, you're multiplying a decimal by a decimal. The number goes down, right? For example, you multiply 0.5 by 0.5, you get 0.25. The number is going down, correct? So it's simply because it's a half multiplied by a half. So your number will go down. And likewise, because our base here is less than 1, so if the power is greater than 1, you have a very small number, correct? But look at the power itself. It's Fy over Fe. So the fact that you have a lot of number for Fe is okay, because now you're going to have the power less than 1. So this number shall go up, right? And besides, it's not your critical buckling stress, it's your elastic buckling stress. And you see this formula will bring it down. This, remember this dotted line here. This is the theoretical curve coming from this formula. So if you use this formula right away, you're going to get this, and you go beyond Fy as we mentioned yesterday. So it's okay, you know, and you should realize by now that if your KL over R is not large, your Fe will be large. And when your Fe is large, you know, this power becomes very small, and instead you're going to have F critical closer to Fy, so to speak. Okay, so we can come back now and try to complete our calculation. Okay, so here we are, critical buckling stress. Now it is, because it is inelastic, so we're going to use this formula, right? 0.658 power of Fy over Fe. And then this number, we will multiply with Fy. And after some calculation music, this is 2060. So not far off from Fy, see, but not Fy either, because of the buckling problem. All right, so is there any question? And P nominal is, of course, F critical multiplied by AG, and it is 2060. The cross-sectional area is 120. That's one big column divided by 1,000. We have 247 tons. But remember, this is the calculated strength, the nominal strength, not design strength. All right, so if it's ASD, you have P nominal divided by factor of safety, and this will give you 148 tons. If it's LRFD, it's VPN, and it is 222 tons. Okay. Any question, please?
Yes, Adam, can you explain again what's the meaning of FE, the number 5,390?
Okay, FE here is elastic buckling stress. Excuse me. This itself is a sort of a theoretical value that we obtain from mathematical approach, right? If you can recall that differential equation. So this elastic buckling stress will not really occur in the real world because of the factors that we discussed the other day. The fact that your material will yield, the fact that we have the residual stress, and the fact that we have the out of straightness problem. So when you use this formula, which is a theoretical formula, you will obtain the elastic buckling stress, which will have to be plugged into the critical buckling stress equation. Is that the explanation you are looking for, or the explanation about the math of this F critical?
Yeah, that's what I'm looking for. So it's not really occur, like.
No, miss. We can go back and look at this. See, you have the theoretical value of elastic buckling stress, but this is not the one that we are going to use straight away. This dotted blue curve is the theoretical curve. It is not the one that will actually occur, because we have those other things like I just mentioned.
Yes.
This is from the idealistic world, you know. We will never have that, because if you can see, if you continue to use this, if you plan to use this, and your L over R is approaching 0, your stress will approach infinity, right? So that's a wonderful thing to have, correct? We don't have to worry about anything. Let's try to make L over R as close to 0 as possible, and we have the strength of infinite. So that's not going to happen, because we have the material that will yield. So we will have this limit, and we have the out of straightness problem that will reduce this curve onto this bow curve. So with all those considerations, somebody developed these two equations to fit the real curve here. And the two equations that they developed is based on this elastic buckling stress, right? So this is the number that we will never use by any means, except in the calculation.
Okay, so we use that to estimate the critical stress.
Yes, critical buckling stress.
Yes. Okay, thank you.
Yes. So this, yeah, I think, you know, I like the fact that you are beginning to use the right word. We predict, we approximate all the numbers in any of your design classes, or, you know, any class for that matter. They're not the numbers that will actually happen out there in the real world. We are in the business of doing something that we call educated guess. We guess, but we guess with proper way. We're not buying lottery, right? We use calculation to guess the strength of our structure. That's why we are not scientists. Scientists would go crazy because they could never get the actual answer of the strength of the structure. They could never. They spend their lifetimes looking for it. So we are folks who make science possible, they say. Okay. Now we come back here. All right. So that's the end of it. And more questions, perhaps?
Yes.
Please.
About the slenderness ratio again.
Here.
When you say the x direction is greater than the y, so the buckling occur in x direction or x axis or something?
Well, yeah, the proper word to say is that the buckling will occur about the x-axis. because when the buckling occurs, your member tends to move laterally, so it rotates about that axis, right? It doesn't move in the x direction. It rotates about that axis.
Okay, thank you.
All right, cheers. Any more question, perhaps? And that question is also good because it is important that you feel the behavior of the structure. Okay. All right. If there is any question, now you are going to face the design problem for the first time. Okay. In the next example here. Now let's conceal the table first. So the question is, now you have the member. Now you know how long it is going to be. And from the analysis, you could probably tell that this is the load that you will design your member for. So from the architectural drawings, you have the information about the length of the member. You have the load from the analysis. But you don't have the member because you have to design it now. Okay. So the fun thing begins here, because if you look at the formula, P nominal is F critical multiplied by AG. Okay. In tension members, you know that your stress is going to be either Fy or Fu. But here, your F critical will depend on, this is the short abbreviation for function for me. Your F critical is a function of KL over R and Fy, correct? As we just did in the previous example. And R here, what is that? That's the radius of gyration. It's a property of the section, correct? This is a section property. You probably know Fy because you select the material. And in this case, we are saying that we are going to use SS400. So we know Fy, but we do not know R. And area of the section, we don't have the section, so we don't know that either. So what do we have here, ladies and gentlemen? Now we have one equation, but two unknowns. So what do we do? In general, in the old days, you're going to have to do something that you probably love very much, that is called trial and error. I know you don't love it. But fortunately, in the past few years, I have collaborated with SYS, and we sort of developed the design table for the members. So I have posted this a few days ago, that we have table A that contains the compressive strength of every member based on TIS on each KL over R. Okay, so we're gonna have that design aid, and I don't think it's beneficial to anyone to withhold such useful information. Okay, so I'm giving this to every student now, and but before we do so, we have to take a look at this. Now, when you begin your design problem, remember that your main equation is always PA cannot be greater than your P nominal divided by factor of safety, right? Excuse me, I should do it better. I think you can see better. It's the same thing, but I just want to write it down here instead of on the same line. That is our design equation, always. Right? So now we are looking for P nominal, but we have here the PA coming from the loading condition. So the easiest way is to move the factor of safety to this side, and therefore our job is only to work for P nominal instead of working for P nominal and then divided by factor of safety. Okay, so I can do this, and that means I now have to calculate P nominal that is going to be greater than factor of safety multiplied by PA, correct? Please notice how factor of safety help increase the demand on the load side. So this becomes 5/3 multiplied by 40 plus 120. So that is 267 tons. So we need to find the section with nominal strength no less than 267 tons. Okay. All right. So now if you look at my table, you see that I have a lot of tables. So you should pick the one with the right unbraced length. Now, another information that we have here is that we know that our member is 3.5 meters long and it doesn't have any bracing. So that means KL on both X and Y direction are equal. And when they are equal, automatically you would know that the R axis is going to be the governing axis, right? Because RY is always smaller than RX. So KL over RY will be greater than KL over RX. So with this in mind, now we have the unbraced length, KL, we have the demand. So we go ahead and look at this column. See, KL over RY. And now because we choose SS400, forgive me, it's quite some time ago, and I was still attached to SM400, didn't change that. So you have KL over R, which should be Y-axis because we don't have any bracing, so Y-axis to govern. And now we know the nominal load. So we just look at this and look until you find the section that has the load more than 267. And voila, I have found one here. See that? Okay. You see that the section here, it just a coincidence. It turns out to be the same section right here. And when you pick this section, you know that the KL over RX will be 26.7. And if you go ahead and calculate, the nominal strength for X direction is 289. But for Y-axis is 268. So see how Y-axis governs your calculation. Okay, so simple as that. We can say that we are going to try this section. Okay, is there any question about this? Pretty simple, right? Wow. With this table, and you know, not only that you can use it, I use it as well to help my life dramatically. So with this, and you know, it is always a good thing that, let's say this table will help you in your prelim process, your preliminary design, to pick up the section. So after we locate this, we may want to perform the calculation one more time, okay? So I can say here, try H 300 by 300 by 94 kilogram per meter, okay? And all the section properties if this is different, you can just go to the table here and pick the necessary properties for your calculation. Okay, remember that we should always do this, because one thing for sure, and this table doesn't help you in local buckling issue. So we should always perform this again. So check. First, it's local buckling. Okay, and again, you need to check a flange, and it is BF over 2 TF, and this is the same. So I'm just gonna go over it quickly, okay? Because the section turns out to be the same, and now you know it's 10, and it is less than 0.56 square root E over Fy, which is 16. The web is H over TW. Remember, H is not D. You can also pick these numbers from the table. It's 23.4, right? Just less than our limiting value of 1.49 square root E over Fy. And it is 42.6 if I remember correctly. So again, we get the big okay. All right. You can tell me if I am going too quickly, because I just think that this is the same as the previous example in terms of the section. So that's why I'm a bit quick. But if you wish to take notes, you can let me know. Okay. Now the second one, it's a lateral buckling, of course. Now you check both axes and you see there might be some of you who struggle to understand why the larger KL over R will govern the design. If that is the case, you can also calculate the strength of your compression member until the end, until you see the P nominal in the end, and you will be able to tell that the larger KL over R will give you less P nominal, and you will see. But you know, it's avoidable, that calculation. So we have KL over Rx. That is 350 divided by Rx, which is 13.1. But you know, I know this is I can say by inspection, this will not govern. I don't have to write any of this, but you know, in terms of academic purposes, you should not omit anything. If you don't want to do calculation, fine. You need to let me know that you know. You don't need to calculate. It's too many words, but yeah. Anyway, you should make a statement like this, that my inspection, this is not governed. This is not going to govern. So I will not calculate this. But if you don't write anything, I am obliged to assume that you don't know. Okay, because you are still junior engineers. You are under practice, right? And KL over RY, excuse me. All right, so for y-axis is again 350, but RY is 7.51. So you see this slenderness ratio surely will govern. So this is 46.6. We go ahead and then now you should know this is less than 4.71 square root E over Fy, right? Because it's 135. And now we can go ahead and calculate the elastic buckling stress. I square E over KL over R square. Don't forget the square terms, all right? Yeah. 9090 kilogram per square centimeter. And therefore the F critical will be equal to 0.658. Power is Fy divided by Fe again, multiplied by Fy in the end. And this is 2230 kilogram per square centimeter. Notice that it's pretty close to Fy. Okay, and therefore P nominal is F critical 2230 multiplied by the area, and this is 268. The same numbers that we have in the table, so you can say, my table is correct. And that's it. End of your design. And see how easy that is. If you don't have information like this in hand, you're going to have to make a guess, unfortunately. Okay. So that's the end of the second example. Is there any question? I realize that we have had the class for 50 minutes, so we should do a break. So we have one more example to finish for the compression member, then that's it. But you see, that we have raised, and we are going to design that one. Okay. So would you like to do this and finish it off, or would you like to have a break first to give yourself some time to digest the idea? I think it's better to have a break.
Please.
All right. So let's have a 10-minute break. Okay.
Thank you.
And we'll come back, say 3 minutes past 10.